Okay, we're going to do section 13.5, which are equations of motions with normal and tangential coordinates. Again, just like before, when we did normal and tangential coordinates, pretty much the same thing, except now we're going to include forces in them. And so just like before, you maybe had something going along a curve and say like this, and you had a tangential component of acceleration and you had a normal component, or you could have like something on the writing kind of on the inside of a curve. Once again, you had maybe a tangential component here. And again, maybe the normal component, possibly is pushing out this way, or could be, probably it's going to be this way, depending upon the application. And just like before, we're going to have f of t equals mat, and f of n equals ma of n. Like I said up here, you can maybe show this way. And now this time, we may, in some few cases, we may also have like what's called a B component, like a binormal component. So if you think of something, say, moving along on some kind of a surface, it's going to maybe be a tangential component and then a normal component this way, and a binormal component B coming out or up like that. We're not going to have a lot of problems like this, but sometimes we'll have to consider this component, so like these two are like in say a disk, and B is coming out of a disk like this. And there's a couple of important things to remember when you consider these kind of forces. We have to get the normal force in the right direction. So let me actually write this down. So when considering normal components, forces are considered positive if they're directed toward the center of rotation. Towards center of rotation or center of the circle, or center of the curve. If they're directed towards the center, then they're considered positive. So let's maybe have a couple cases here. So let's say you have a car or something going around a curve. And so maybe this is a car and it's going with some velocity in this direction. And so this is your center of rotation. Again, it could be a circle, or it could be some general curve. Remember, we had rho from before, the same as before. This is our radius of curvature. And if you have, let's say if you put your normal force here, I think in this section, I'll try to use the book's notation. I think you use like NC now for the normal force in this context. You can use N, NC, NA, whichever you're comfortable with. So now in this particular case here, so let's say, you have a mass here, however many kilograms, let me just call it M. And so let's say if you're in SI units, and let's say if you sum the forces in the N direction, in the normal direction, it's going to be mass times A normal. And now in this case, so when we're looking like this, since the normal is considered away from the center of rotation, it's going outward, it's going to be negative. So it's going to be like, this will be like mg minus nc equals your mass times your a over, and of course a over n is just like before. Remember, that was velocity over radius, velocity squared over radius. So if it's pointed this away from the rotation, it's considered, you put it negative in the equation, the way to think of it. And then on the other hand, if let's say you have actually, that's not a good picture. Let me do another one here. Slide this up a little. What I want to do is maybe have, let's say, a car is maybe like here, and it's going once again with a velocity in this direction. And you have, like I said, the radius of curvature here. And so your normal force will be in this direction. So again, now since that's sort of going towards the center rotation, it'll be like put in positive when you put into the equation. So Fn MAN minus mg. So again, if we're calling it this direction positive, then we'll call the other direction negative, plus nc equals m v squared rho, like this. So it's kind of important to keep that in mind. So let me do some problems from those fundamental ones from the book. Unfortunately, I did copy some problems for you. I forgot to copy the fundamental ones. But if you have your book, you can open it. If not, I'll show it on the screen here. We're going to now look at this problem. It says the block rests at a distance of 2 meters from the center of the platform. If the coefficient of static friction between the block and the platform is 0.3, determine the maximum speed which the block can attain before it begins to slip. Assume the angular motion of the disk is slowly increasing. So notice that they say the angular motion of this is slowly increasing. They say that so that you can assume that the tangential velocity is very close to zero. Excuse me, the tangential acceleration is very close to zero. So we can assume a sub t is zero if the angular motion is slowly increasing. So we have kind of a picture, maybe something like this, from looking from the top. And again, you have like This would be like the normal direction and the tangential direction. Then if you look, so this is the top, and if you look from the side, you have maybe something like this here. Where once again, this is the normal direction. And this is what would, like I said, we call that B direction or binormal direction. And then like friction is sort of operating, say if it's going around, it's going to try to come off. And friction, again, is going to be mu times, again, whatever you call this at the bottom here, maybe NC. And again, the radius was 2 meters. So again, the first thing we want to do is find NC. So if we sum the force in the binomial direction, and if we call upward positive, again, we're looking at this picture up here. And so you're going to have the mass, and you're going to have this NC here. So let's say this could be NC minus then the mass of the thing times G is equal to M. And of course, in this B direction, it's not going up or down, so the acceleration is going to be 0. So you can say this NC is going to be mg. And so we can start with that. Now, if we sum the forces in the normal direction up here, so this is the normal direction here, and if we call, yes, let's, N equals M A N, like this. And really the only force that we're going to have on this thing it's just sitting on top of this disc. So the only force we're going to have is our friction force. And that's going to be mu times NC. MAN. And we're told mu is 0.3. And we said from over here, we said NC was mg. AN. The m's will cancel. And if we use 9.81 for G, then AN is going to be 2.94 meters per second squared. And then so that gives, so in other words, this is the greatest normal acceleration that we can have to keep the block from slipping. So let's note that. Before the block slips. And of course, then we just need to see what velocity is associated with that. So then remember AN is going to be the velocity squared over rho. And so it's going to be 2.94. And velocity squared, we're told that rho is 2 meters. And so velocity is 2.43 meters per second. Any questions on that? Any questions at all? Pretty straightforward problem, but it's pretty useful because this has a lot of ideas in it. And so let's look at F13-8. Now we're going to take a look at this problem, F13-8. Determine the maximum speed that the Jeep can travel over the crest of the hill and not lose contact with the road. Notice rho is given as 250 feet. A couple things to note, like the road is going to be, the normal force this time is going to be upward, like away from the center of rotation. In the last problem, we didn't have it. Remember, N wasn't on anything curved, so we didn't have to take that into account. But now it's going to be like at the top of this curve, pointing away from the center of rotation. So when we put it into our equation, we'll have it like as negative. So let's do that. Again, this is F13-8. And so once again, you have maybe a picture like this. And again, this is, I guess, English unit. So we'll call this like, it has some weight of some kind. You don't know what it is. I'll call it just WT, just some weight. And it's moving along with some velocity. And as I said, since it's pushing on the ground here, so do your normal force in this direction. So if we sum the forces in the normal direction, F equal ma. And again, like I said, when you put this in, it'll be in as negative. So again, so kind of like this, let's see, like this direction is going to have to be like positive, so to speak, because you were saying that that's going to be going negative. Again, there's other ways you could formulate this. I just kind of always go with this specific way of doing the signs. So in any case, this is going to be then the weight is going to be 1/4 the weight of the car minus this normal force equal the mass. Remember, if you're dealing with weight, mass is going to be weight divided by gravity times the normal force like this. And again, if you have something moving like this and you have a force up here, as long as this force is positive, that means that the car will stay on the road, but there'll be separation. The car will leave the road at the point when NC is 0. So therefore, let's put that in. So that's going to be really the point where it'll separate then and just go here. There'll be a T over GAN. This will cancel, and this will cancel. I'll leave this with 1 on this side. So AN equal to G equals to 32.2 feet per second squared. So once again, this would be the maximum acceleration before car leaves road. And so once we know that, then we can, just as we did before, find our velocity. 32.2 velocity squared. And we're told the radius was 250 feet. And put that in your calculator, and you get 89.72 feet per second. $13.50. And actually, your book has another part of this question, but it didn't make a lot of sense, so I cut it off. So let's take a look at this. So we're told this car A has a mass of 0.75 kilograms, attached to spring, 200 Newton meters, rotates about the vertical axis in the rods. So you can see what's kind of happening is it's a spinning, and it's spinning. It's going faster and faster. This weight is going out from the center, and so we have to calculate. We want to know what speed we have to get to make S equal to 100 millimeters. So we want to know how fast we have to rotate. In other words, the faster we rotate, the farther this is going to go out. So we want to find out the velocity to get S equal 100 millimeters. So let's take a look at that. So this is 1357. So let me take a look at it from, say, the side view. And again, we want to find out what it's going to take for that to be out at 100 millimeters, 0.1 meters. And our spring constant is 200 Newton meters. So again, we'll sum the forces in the normal direction. Again, so this is right here is like the center rotation. And so do this. And again, really the only force in the normal direction, it's not sitting on anything. Apparently everything is smooth. The rod is smooth. And so the only force is the spring force. So let me just note that. So F spring. N. And again, we're told 200 Newton meters. So we can do 200 times S, huh? So it's going to depend upon what S is. So the farther out it goes, the more spring force. And we are told it's 0.75 kilograms in AN. And so calculate, and also they want to know exactly when it's a 0.1. So if we make that 0.1, AN like this, AN is 26.67 meters per second squared. So basically, this is the acceleration required to keep the collar at 0.1 meters. To keep maybe S equal to 0.1 meters per 100 millimeters. So once again, once we got that, just do actually what we've done in all the previous problems, I guess. Use this equation, find out what our velocity is. And also notice when you look at the picture, if you look at, say, from the top, that S will end up being our radius as well, won't it? Because that S is measured from the center. So say the radius we're interested in is S equals 0.1 as well. So 0.1, put that in your calculator, 1.63 meters per second. Any questions on that? Okay, let me do another one here. Let me do one of the another one of the car ones that's a little bit different right now. Let's do 13-69. 13-69. Next, we're going to look at this problem. We have this 0.8 milligram car traveling over a hill, and we're given the speed, and we're given the acceleration. The speed is 8 meters per second, acceleration is 3 meters per second. Determine both the normal force and the resultant friction force that all of the wheels of the car exert on the road at this instant. And we're given the equation you can see of the hillside, this y equal 20 times 1 minus x squared over 6,400. And there's a lot of features in this one as well. Again, this time it's not a fixed radius, so we're going to have to calculate this and use the stuff we did previously. So again, you have some kind of a curve here. And point A over here. And we given like a velocity. And we're told that this is 80. And of course, that's going to be like 80 and 0. So our point A is going to be yeah, like 80 meters here. So it's going to be at 80 and 0 is going to be the coordinate. It's going to be Y. X here. And we're also told this curve will base that equation 20 minus x squared over 6400. If we multiply that out, we're going to end up getting 20 minus, when we divide the 20 into the denominator, that's going to be 320. This. So again, we're going to have to use that equation to find our curvature. Remember that long equation? So we're going to need the derivative. And so we have to do dy dx. And we bring the 2 down, divide that into that, we get minus 160. So it's going to be x over 160. G squared y x squared. Take another derivative. That'll be minus 1 over 160. If let's evaluate those at our point is 80, huh? So dy dx evaluated x equal 80. And you can see that's gonna be like minus a half. X equal 80, and it's like minus 1 over 160. So now we can put all those into our equation for our curve. Remember that was at 1 plus dy dx squared 3 halves with this. And that's going to be 1 plus this thing over here. That's 1 half squared to the 3 halves. And then the absolute value of this in the bottom. Calculator, I got 223.6 meters. And now one thing, so if we actually start looking at the forces, we're going to need a little bit more information now. So if you kind of think of just at this point here, where this car is moving along, at this point A, we're gonna have to figure out like forces in the x and y direction, or the normal and tangential direction. So thing is, we're gonna have to figure out what the slope is, and you remember, of course, the slope is gonna be dy dx. So the slope, remember from calculus, is always gonna be dy dx, and evaluate that point A, which was x was equal to 80. So our slope is minus 1 half. So that's like, so that's like our rise over run. So we're going to go, and since it's negative, we're going to go down 1 and over 2. So you can sort of think of it, maybe make a little triangle here, down 1 over 2 like this. And so to find theta, of course, we can just do the tangent, huh? Tangent theta is going to be 1 over 2. When we put that in your calculator, if you do the arc tangent, I got like 26.6. 26.6 degrees. And so, so first of all, let's find the normal force. So again, so let's say this is the normal force is like over here. I don't know if you want to call it NC or NA, whatever. That's the normal force. And we have that the car is like 800 kilograms. And I'm going to go ahead and redraw this picture now. We had just a second ago. And let me make this a little bit nicer like this. Again, we're going to have our 800 kilograms going this way, and then the reaction is going to be this way. Now, of course, you remember that if it's going away from the center, if the normal is away from the center, that's considered negative. So that means that this direction is negative. So that means going this direction will be positive. So again, we're going to focus again on the normal direction right now. So we sum the forces in the normal direction like this. And now we said this was 26.6 degrees. And then that's also going to mean this one right here is going to be 26.6 degrees in there. And that's precisely going to be the normal component. In other words, if we sum the force in a normal direction, we'll have 800 times 9.81 cos 26.6 degrees. Again, that would be going this way. And then opposing it is this negative. We're calling NC the normal reaction. And again, the mass is 800 kilograms. And our velocity was 9. And then we also determined that the rho was 223.6. We calculated that a minute ago. So remember, this is v squared over rho for the normal acceleration. And when you put all that in your calculator, you get that NC, the normal, is going to be 67.27 newtons. Like this. So, and let me just mark here. So what we did, we considered this direction to be positive. That'd be going this way because we said this normal was out from the center. Something out, moving out from the center is always going to be negative. And so let's also look in the tangential direction. Again, we're going to have something like this. I won't put the curve in just to keep from cluttering. So once again, we're going to have this 800, 9.81 going down. We're going to have a friction force opposing this, call it F sub F. And as before, normal is going to be in that direction. And so let's take a look at this. So again, if we sum the forces in the tangential direction now, and again, you can pick whichever direction. I'll call this direction positive this time. And so again, we said since this direction was a cosine, then the tangential direction, which would be like going this way, must be the sine. So let's sum those up. So we'll have 800 times 9.81 times sine of 26.6 degrees minus the friction force, F, going to oppose it. And those are really the only forces we have. And so this is going to be equal to the mass, which was 800 times the tangential acceleration, which was 3. This was given. And if you put all that in your calculator, you get the tangential force to be 1114 newtons. I should say, excuse me, not the tangential, but that's actually the friction force. Like that. And those were the two things we were asked to find in the problem, the normal force and the friction force. Actually, I suppose it didn't ask for it, but since we know the friction force and we know the normal force, we could probably also find the coefficient of friction, though it doesn't ask for that.